Hello, my name is Tian, a ship intern working under Dr. Peter Bocage. Today, I'll be talking about my work on procedural model generators for an RSoX simulation suite. Over the summer, I developed a software library to abstract the morphology creation process for a resonant soft X-ray scattering simulation suite. The library is capable of creating individual morphologies, choosing points within arbitrary space, tiling morphologies at those points, and serializing data to disk for the simulation. The library is simple and easy to use, and also provides features such as collision detection. My project involves a software simulation suite for resonant soft X-ray scattering, RSoX. RSoX is a small-angle scattering technique similar to small-angle X-ray scattering and small-angle neutron scattering used to analyze the structural characterization of nanomaterials. RSoX is unique in that it is capable of determining molecular orientation due to sensitivity to soft X-ray transition dipoles, allowing for the establishment of processing structure performance correlations. NIST has a simulation suite called RSoXS, which allows us to digitally simulate the RSoX scattering process using voxels, or values on a regular grid in 3D space, and then analyze the simulated scattering patterns. The simulation takes multiple parameters for different types of morphologies, meaning that a user will be creating lots of data. The current lack of abstraction in the morphology generation process means that you have to hardcode each individual step, such as voxel placement, voxel alignment, voxel tiling across larger surfaces, and serializing data to disk to run the actual simulation. This means that depending on the complexity of the model you create, the code you write can become very long, messy, and difficult to maintain. My project was to build a software library to alleviate these issues by abstracting the morphology creation process. I target 4 key areas: the creation of an individual morphology, choosing points within an arbitrary space, placing the morphologies at those points, and finally serializing the data to disk for the simulation. I aim to keep the library easy to use and maintain, allowing users to add extra functions for generating points, preset morphologies, while still providing easy access to abstraction object internals to modify underlying data, such as if you wanted to still manually create your own morphology or only use specific parts of the library. The library abstracts morphologies into shape objects, which are containers for Euler parameters defined for each present material number. The Euler format has 4 parameters. Volume fraction defines whether there is volume, either 0 or 1. Aligned magnitude represents the alignment magnitude on a scale from 0 to 1. Theta is the angle of rotation about the y-axis, and psi is the rotation about the z-axis. Each material in a total morphology will have these 4 Euler parameters. For example, a certain z-axis slice of a sphere made out of material 2 would look like the image on the right. To create an individual morphology, we follow 4 steps. First, we create our volume array. For a sphere, this would be defined as all the points within a certain radius. Then, we create an alignment array. For a sphere, we want all of our voxels that have volume in them to be fully aligned. Then, we calculate the angles using inverse tangent. Theta will be y over x, while psi will be r, or the square root of x squared plus y squared, divided by z, with the coordinate 0, 0, 0 being defined as the center of the shape. We can also apply rotation, but this only applies to non-isotropic shapes. The library has out-of-the-box functions for following this process to create spheres, core shells, and ellipsoids of any material. We can also generate any number of randomized versions of these shapes by providing a range for the parameters, such as if we wanted to create 100 spheres of random radii. The library has point generation algorithms that we can use to create points to tile our shapes at. The algorithms we can choose from include Poisson disk sampling, uniform grid, and random offset grid. Poisson disk sampling will place random points but ensure that they are at least a minimum distance away from all other points. Uniform grid will place a point after traveling some distance in one dimension, similar to the pattern of a square lattice. Random offset is the same as uniform, except all the points have their position randomly offset within a certain range. To tile our morphology, we provide our list of shapes and points to a grid generator object that will choose a random shape from the list to tile at each point. We can also tell the generator how to react if it detects a collision between 2 shapes. Either it can overwrite the already existing data, or skip the point and not tile the shape. The simulation takes files in the HDF5 file format. To serialize data, an HDF5 generator object provides a one-line method to convert a shape object into an H5 file. All we provide is the file name and shape object, and the library will automatically write the appropriate groups and datasets to the file. As a use case example of the library's capabilities, I utilized the library to recreate the already existing tutorial for RSoXS. The tutorial consisted of randomly placing a core shell morphology throughout a 128 by 128 by 32 voxel space. Using the library, the amount of needed written code was reduced by over 80%. The original was over 40 lines long, while the library needed only 7. With that, I'd like to thank my mentor, Dr. Peter Bocage. I would also like to thank Dr. Peter Dudinas and Dr. Dean DeLongchamp for helping guide me on this project and for providing extensive design feedback. And finally, I thank Churns and the NCNR, along with the internship directors Julie Borchers and Joe Dura for making this opportunity possible.